that was in here. Yeah, get in. Hello, everybody. Enjoy that. It looks good. Yeah, when you carry on eating, don't worry. That stops you asking questions anyway. Ooh. He's my favourite as well, to quote Bruce Forsyth. There we go. You know who your friends are now, don't you? He's got lots of knives in his back. Right, okay, so congratulations, you made it through to the last lecture, you few diehards, you, well done. So I hope you've enjoyed it. A couple of the slides didn't quite show as they should have done this morning, which was why I looked a little bit more off-piste than normal. So one of the things I just wanted to highlight was something that was missing on that. There are lots of textbooks, and there's lots of stuff you can look up. But those of you who are doing design project, I wanted, when you're talking about zeolites, the Bible for zeolites is Breck, which is that book there. It's a dark black book. It's about so thick. It's got silver lettering on it. It's in the library. It's very, very good. It's way, 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 way over the top for you guys, okay? But on design project, some of you will be wanting to know a bit more about the Catalyst, and you'll look it up in Google, and you'll see lots of stuff. But they do have hard copies of Breck in the library. Also, young Stuart Holmes has a copy in his office. So if you want to see Stuart's got a copy, because I referred to it the other month or so, and it told me something I didn't know. And I was fighting a patent lawyer at the time in America, and I was trying to justify why I'd done a particular procedure a particular way, and it was different. And I got my evidence out of Breck, and the patent lawyer went away. Found something else wrong with it, but that's a different story. So patent lawyers will do that. So textbooks for design projects that are dealing with steam reforming or shift or low temperature, high temperature shift, methanation. The book you want to be looking at is the Catalyst Handbook by a chap called Martin Twigg, T-W-I-G-G, Twigg, Martin Twigg. Now Tom Rogers, who is a man of fame who follows me, and I had to listen to Distillation this morning as I assessed his teaching. It wasn't bad, and he tried to make distillation exciting. Not possible. But anyway, you stuck with him, and that was good. And he was a good lecturer, and it was pleasing to see him, because I knew him when he was a PhD student and when he was in my class doing CRE3 a few years back. Okay, so what goes around comes around. So funny that we should follow one another, and I do his teaching assessment. So that was a nice thing for me today. So key thing on this slide, Catalyst Handbook, Martin Twigg. Don't forget it. If you really want to know a lot more about zeolites because you're interested, then that's the ultimate textbook. What else can I tell you? So the key diagram I wanted you to look at there is to think about the diffusion regimes, and it's that slide there. So that was the one that didn't appear by animation. I have no idea why it didn't appear by animation, but it didn't. And you're talking about the effective diffusivity or diffusion rate, diffusion of centimetre squared per second through a pore of particular sizes. Note it's clearly an engineering graph, because it's got linear scale. It's got 10 to the factor of this on one bottom axis, so you've got a log on the bottom axis, and you're going up or down in orders of magnitude, of 2 orders of magnitude each time. So molecular diffusion. The pore is so wide that it's likely that a molecule, will bump into another molecule, and a reaction may or may not occur. That's molecular diffusion. The range of Knudsen diffusion means that you're narrowing the pore, so it's becoming more and more likely that a molecule will interact with the wall of the pore bump. But it could still interact with another molecule, but could interact more with the wall. So you're now interacting more with the wall of that pore, that inkwell. As you get into configurational, zeolites are actually, and I'm making a mistake Tom did this morning, zeolites are just about here. Okay? They're on that border between Knudsen and configurational. Now, configurational diffusion is not explained particularly well anywhere, because they sort of don't really explain the concept. But if you think of Knudsen diffusion and the pores narrowing and narrowing, eventually on the borderline where it's configurational and Knudsen, you're getting the molecule is the only thing in the pore. So now it must interact with the wall. And that's really all there is to know about that. Been an exam question for 3 marks and 2 marks every year. Good luck with that one. So everything appeared on that slide. So remember what we were talking about? I didn't bring the model this time. All I want you to get across is the concept of the molecule in the pore. So the molecule in the pore. The same distance across here, distance here. So there you can see that that thing, which is a benzene ring or a toluene molecule, is stuck in the pore. It's going to touch the walls. It's not going to touch another molecule. It's much more likely to touch the pore. Okay. Did we understand product selectivity and reactant selectivity? Possibly not. So let's just look at it again. What it means is the shape of the molecule that you're reacting doesn't fit through the pore. So the case of the branched one at the bottom, which is the isobutanol, it doesn't fit through the pore, so therefore it doesn't do anything. The other one fits through the pore, and we get dehydration, so we're losing water. I think now you've got the concept, because you've seen the figure a few times, about the molecule fits in the pore. Product selectivity is exactly as it says on the tin. The thing that comes out of the structure is the thing that you want, but nothing else does. That's what that's trying to explain. I did that one. Refinery. You've got the idea with the refinery, you've got the idea where the zeolites and the various bits and pieces go. Any questions in particular that might relate to design project or relate to that schematic on that? Because I put that there for a reason. You don't have to ask a question. Okay, so you got the idea that you might want to know what's an oil fraction, and you might want to know how it's broken down, and we might want to know what it goes into, but the key thing Arthur's looking for are the processes that the zeolites are involved, which are the white boxes, for those of you who didn't notice that this morning. And that's where we stopped. Notice that the things coming off the fractionating column are pretty much the same as were described on the other diagram. There's light gas, there's gasoline, there's cycle oil, there's heavy gas oil. And what you're basically reacting in this FCC unit is the gas oil. Now, if the riser cracker is the long tube, which is 5 meters tall and about half a meter in diameter, let's say, the regenerator is a hell of a lot bigger than a drain pipe 5 meters high, or a big drain pipe 5 meters high. And that's your problem with this process. The regeneration process is slower than the reaction. Engineers should know probably that the catalyst deactivates on the way up, it goes into the regenerator, and the coke is driven off. If you get rid of the coke, i.e. the carbon on the catalyst that's caused the activation, it's an exothermic process. So it gives back heat. The cracking is an endothermic process because you're breaking bonds. It makes sense to understand when you form bonds, it's generally exothermic. When you break bonds, it generally, well, it pretty much always is endothermic. So this process is economically balanced on the heat balance, not on the products. It works purely because it's balanced on energy, and therefore it breaks even, and you can say that the process itself is energetically neutral. But the reaction is highly endothermic. The catalyst is dead in 15 milliseconds to 100 milliseconds. How on earth can you design a process like that and live with it for 70 odd years if it doesn't make you a shed load of money? And the reason it makes you a shed load of money is because the regeneration cycle generates the heat that balances your process. So it's an important lesson, and I'm stressing it for a reason. In design project that you're doing and you're about to engage in fully, it's when you iterate your reactor and your heat integration and your mass balance. Your mass balance you'll get right, probably. Your heat integration depends on what you're doing and what reactions you're breaking and what making and what you're doing with that. You have to iterate and keep iterating, and that's the purpose of design. Somebody asked me the other day, what is design, Arthur? Do we get one only solution? Because our groups work to one only solution. And I said, no, you don't get one only solution. You can have several solutions. You can look at the steam reforming process, and you can look at methanol synthesis process, and you'll find that you can optimize in different conditions. You'll end up with different numbers. So one person will work out a number and say, right, we've got to work with a feed to cat ratio, a catalyst ratio to feed. So in this one, the catalyst to feed ratio is 6 to 1. You've got 6 times more catalyst than feed. Think about that. A catalytic process is supposed to be something that speeds a reaction up. So why the hell have we got 6 times more catalyst than we actually have of the stuff that we want to break up? That's not a very good catalyst then, is it? With your immediate reaction, you've got 6 times more catalyst than the thing that you're trying to turn into your valuable product. But that's what the process does. And that's the way it is. Okay? Because it's dead in 10 milliseconds or 100 milliseconds. So you've not got to have quite a bit more catalyst. Well, now, you wouldn't have thought that as a logical conclusion of design. You would have said, oh, Arthur's told us about catalysts. They speed up a reaction. We're not supposed to use a little bit. We're not supposed to use a lot. Think of another example, which you may find useful. The PET bottle I referred to before. Or the plastic bag that I put my sandwiches in. To be correct, my wife put my sandwiches in this morning. Sorry, darling. It's on video and tapes and everything. Better get it right. That plastic film contains a ppm, parts per million, level of the catalyst. It's in the plastic. You can't take it out. You're sacrificing your very expensive catalyst and leaving it in the plastic bottle that you've got in front of you or the plastic bag that my sandwiches were in this morning. So it's got to either make you a shed load of money or be very, very efficient to do that. And of course in plastics it's ppm, so it's very, very efficient. So your polymer reactants to catalyst is now extremely high feed, very low catalyst. Completely the opposite of this process. Both those processes are the mainstay of the chemical engineering business and the mainstay of most processes, because you're making polymers, and if you don't make polymers, where do we go? Well, probably most of us are naked, and that's not a good concept, I know, so let's not dwell on it. But most of us will not be wearing very many clothes that haven't got polymers in them. If you take away the plastic and you take away the oil, we're not moving anywhere. So basically we're back in the Stone Ages. And that's really this society that you're designing, okay? So it's more philosophical than it is design, but think about that. You've got complete opposite ends of the scale with FCC process and polymerization. Completely the opposite end. And yet they're the mainstay of our lives. One's extremely sensible, very small amount of catalyst, making a very light product that goes a long way and is used, and the other one drives cars around. Where would we be if we couldn't drive around? It used to take 3 weeks to get to Europe, for example, by the normal routes. Come on, there we go. So the last bit of the slide just reminds you that this is an energy process driven. It's very high intensive energy in, and we get a lot of energy out on the regen. And that's what you need to remember if you're on interview around FCC. So design gives you many answers, some of which are right, some of which are ludicrously wrong. If you make a ludicrously wrong decision in design project, but have justified it with your approach, you can get as many marks as somebody who does a brilliant design. You won't get the top mark, but you will get as many marks. So don't panic if you come up with a ludicrous design or somebody's made a mistake and it's obviously wrong. Now, you remember before I talked about this time scale? Okay, so this is the point when zeolites started to be used. If we draw this line further back to 1923, that's when sand was used. So sand, zeolites, Arthur spends his whole life tweaking zeolites, and he retires. So that gets us to 2024, and you'll be in your 30s perhaps, near enough. Yeah, you will. So those are the developments. So I'm not going to get rich making a new catalyst. Yes, young man. Yes. I hate to tell it to you, but if I come up there and beat the hell out of you, which I won't do because you're stronger and more physically adept than I am, and you can probably run quicker, that took a lot of energy to do that. So I'm trying to knock lumps off you. Why would that not be an endothermic process? So breaking bonds is most definitely endothermic. You need energy to break carbon-carbon bonds. You can't do it any other way.
It's making bonds.
Making bonds, I should have said, was more likely to be exothermic because you're forming bonds. So think of polymerization. Polymerization is joining carbon units together. It's very exothermic. Okay? If I missaid what I said, I apologize. I have a Mancunian accent, and endo and exo do sound the same if I say them quickly. So it's perfectly... That's all right. Nice to see you. He came in, big smile, and went again. Bless him. Right, so gasoline composition. So what are we trying to say about zeolites? What do they bring to the party? You got the idea. The molecules just about fit inside the structures. The structures, therefore, are known as molecular sieves. Just remember that term, molecular sieves. So if we use them, we would hope we'd get some benefit. So the graph at the top is trying to show you amorphous silica alumina. That's sand with alumina in it. Okay, so it's got no structure. The surface of it is just the surface of the thing that it is. So there's no internal workings to it, it's just silica. So when you use amorphous silica alumina, which is the predecessor, so we're here, it means that you would have to have an additional capacity because the catalyst itself is not very good, but actually because of zeolites, you're getting more product out of your barrel per day is what this graph is trying to tell you when you use the zeolite. But the thing I'm interested in, and not the picture, and I actually found the original source by accident the other day when somebody asked me a question, that diagram. Gasoline composition at the top. So we want better engines, we want better RON, we want to change things so that the car runs better. Aromatics are predominantly used to increase the research octane number of a car. Benzene is the classic one. Benzene is now banned or is being slowly eradicated from petrol. That benzene used to be 15%. 15% when I was a lad. Benzene, for those of you who did the environmental course last year, know that benzene is probably one of the most toxic things you can have, allegedly. And I'm not saying it isn't dangerous, and I can't buy it, and I'm not supposed to have it in the lab, even though it's one of the things I used to wash my hands in when I was about 16, and most mechanics would have washed their hands in it to degrease. It's a common degreaser. They've got rid of it now and done something else. For those of you who are seriously concerned about me, the latency period for cancer is 40 years. So I'm about due in about another 2 years, so keep your fingers crossed, won't you, please? But that's the truth of the matter. Things that were dangerous back in my youth were completely different. Asbestos, yes, has always been around as dangerous, but benzene, no. Benzene was a paint thinner. My dad used to put benzene into his paint, his Dulux gloss paint, and he used to paint a house with it. He was cheap like me, but don't tell anybody. He used to thin the paint. So what are we doing there? We're making more aromatics when we use the zeolite. We're making less saturated ring structures, more aromatics better on, more paraffins, less olefins. Importance for engineers. Stable feedstocks, stable things. Olefins are reactive. Paraffins are not so reactive. Olefins tend to be reactive with things like oxygen and go off and things like that. Refiners love stable products. So the fact that you reduce the olefin content and you reduce the naphthene content but increase the two things you want, which go into gasoline, which is naphtha in the range of C5 through to C8 hydrocarbons, then that was a massive leap forward. In 1988, they made another leap forward, and they added this thing, which is ZSM5, which is the structure that I was passing around this morning. And by adding this ZSM5 additive, they improved again the product that they wanted. Notice the graph. I'm only drawing your attention to the graph. I'll talk about MTBE in a minute. So we want gasoline because that's the thing we sell, yes. But what happened since 1988 that is very, very obvious to us all? Plastics. Everybody wants plastics. So the more olefins that you can get, the more butenes and the more propene you can get, the more you can turn it into other molecules. Now, in a refinery sense, this is really, really important. So we started off by saying zeolites give you more gasoline, and that's great, and less olefins. But all of a sudden, the refiners went, oh, hold on, gases. I didn't define what gases was. Within gases, you've got C3s and C4s. They're olefins. Those olefins, produced by this guy, ZSM5, go into polymers, but they can also do the reaction that your man asked me about, carbon-carbon bond formation. They can be oligomers, so they can make bigger molecules. So anybody doing a methanol to olefins project will have a bit of a problem if you're doing methanol to olefins. The reason is your methanol will dehydrate, give you dimethyl ether, then it will go to C2 olefins, according to you. Yes, it will. But C2 olefin is very, very reactive, so it will make C4, C6, C8, C10, and on and on and on it goes unless you stop it. So the fact that they make those materials means we can make bigger molecules. So when you get the gas product, they want to make more gasoline, but they also want to make polymers. So now the refiner's got an advantage. It can twist its feed, and it can twist its product stream to make either polymers or gasoline or an additive for something else. And that's what that's all about. Now then, that's a simulation of the zeolite wire with the ZSM5. That's how it's normally shown in your guys' language. And we've got to the top, and we've got various chemicals, and a little compound called MTBE is mentioned up there. But the streams, C3 go off to make chemicals and polymers. C4 stream goes off for alkylation to make octane that goes into cars. So refineries are very, very interesting places when you get to be my age and you've done it long enough. Maybe not so in yours, but every little bit is reworked around to make as much out of every little carbon molecule you can get. So if you've made too much gas in a process, oh, I know, we'll redirect it somewhere else. And they redirect it to chemicals if there's a polymer demand. If there's a chemical demand for gasoline that's have a higher octane because there's more BMWs in the world, we go down the alkylation route. Enough said. So now we're talking about coking. Commonly misspelt into something else when we're on Word, but anyway, please don't misspell it. I've stopped you writing essays, so you generally don't misspell it into something rude. But my two PhD students who are just doing their vivas this next week have misspelt it all over because it's auto-corrected. So, coking, parallel channel system versus a three-dimensional. So this morning I talked about mordanite. Mordanite looks like that. ZSM5 and zeolite wire look like that. If you've got a three-dimensional channel, like you see there, you can see that if you block a couple of holes with coke, there's still a diffusion path. It's more tortuous, the little dotted line is saying that with the arrow on it. It's more tortuous, but it's still possible to get some conversion. This one, however, dead as a doornail. So what is coking then? It's a deposition of carbon. So you go, okay, what do I care about that? You care big time because if your catalyst deactivates very rapidly, you've not got a process. If the catalyst deactivates because of coking, you then have to regenerate it, and you care because in FCC, for example, they just burn it off. So you get your catalyst back. But you still need an extra 25 to 40% per annum catalyst than you started with because it grinds itself to death. Because every time you use it, it goes back in the process and around and around and around and around and it goes. So you end up with attrition. So I'm reminding you of these things because this is how catalysts die. Okay? So we've got deactivation with coking. Coking blocks the pores. That's how it works. But you'll say, oh yeah, it coats the surface. But it doesn't just coat the surface, because if you coat the surface, there's still 9 times on the inside, bigger than there was on the outside. So you've got to coke the thing there. So if asked, how do catalysts deactivate, you might use an example of how things coke and how 3-dimensional pore structures coke compared to 1-dimensional pore structures. I'm just suggesting. So, now this causes a little confusion. So coking, deactivation due to coking, rapid coke deposition, so that's carbon and carbon-related materials. It's not fouling. But fouling can be related to coking in the sense that you can have big molecules in there, and some people refer to it, as you see on the screen, as soft coke. So in other words, a big molecule, like a triple ring structure, gets stuck in your pore. You can't do anything about it until you heat it up and crack it itself at a higher temperature. But it is therefore reversible. So there's reversible coking, soft coke, versus irreversible coking, which we will call hard coke. Everything on that slide is as it sounds. What is coke? Well, it's hydrogen deficient. It's a big molecule, so it's got less hydrogen. Those of you who were here last week may remember that I said a typical organic molecule is CH2, because you have a long carbon chain, so it's effectively got 2 hydrogens to 1 carbon is CH2. When you get to an aromatic, it's CH1 ratio, so the C to H is 1, so you've halved the amount of hydrogen in it. The further and further you get to carbon, the lower and lower the hydrogen gets, the more you go to 0.1. So you go from 2 to 1 ratio of hydrogen to carbon down to 0.1. Obviously, if you're going from 2 to 1, you've got soft coke, because these are more likely to be the aromatics and the naphthenes. When you get to this kind of coke, you're depositing something similar to graphite. So you just imagine it as carbon. But if you said, well, coke deposition equals carbon deposition, you're no students of mine. So I wouldn't expect you to say that in an exam. What does it do? It affects the diffusivity and it affects the activity. So the diagram, which was the schematic, showed blocks in the pore structure. So that hits the diffusivity. The block could be a thin layer with a big lump. The block is just a schematic. It does not have to say that the pore is completely blocked, but it will deposit on all the surface that is active. So it's going to coke up and therefore decrease the number of active sites. We know in zeolites that the active sites are the aluminium sites with an oxygen bond and a hydrogen counterbalancing the negative charge. So you know about active sites. You know about the pore model. You know that zeolites have pores and that the architecture of a zeolite will influence how much it cokes. Can you regenerate? The answer is yes. On the top one, you can probably use heat, plus a gas. On the bottom one, you need to use oxygen. Or air. Remember, engineers, that when you see things that are oxidized in literature and it says oxygen, oxygen's very expensive, air is cheap. Air is cheaper anyway. Compressed air is generally available around the place on a site. Try not to spontaneously combust yourselves when making the process. There's always a rule there, I think. Whoop. So, unbelievably, that seems to be the last slide, much to my amazement. I have a whole course that I could give on that, so I'm just going to check there isn't some mistake that I've finished so soon. As love you as I do. Oh, I did say I would cover one more thing, didn't I? And I've just seen it there. So let's just check I haven't missed anything and jib-chiff. No, I haven't. Very good. So, I want to cover one thing I skipped, which was on analytical integration down the bed, which I said I would cover. And I've put it up on Blackboard, so I don't know if anybody's been and looked, but within one of the chapters on Blackboard, there is an Excel spreadsheet, and there is a slide presentation that I've used before, which I'll try and find in a second for you, just to talk you through a little bit of a design. But if not, I'll show you the design model, and we can just talk around it for 5 minutes, because I think you'll find it quite interesting. So what I'm hoping you've got out of this last 2 lectures, and possibly a little bit from the week before, is an awareness of catalysts and supports. It's aware of the key properties of those, which is really surface area, pore structure, and activity due to acidity, and what the kind of active sites are. I wanted you to look at steam reforming last week. We looked at steam reforming with some analysis. The tools that you can see that I used last week are very helpful in understanding zeolites, but also other materials. So they were the SEM, the TGA, thermogravimetric analysis. Hopefully now you see burns off the coke, and you can measure what temperature it burnt off. You can measure the amount of it. You could use a DSC, which is a differential scanning calorimeter, to determine the exotherm when you burn it off. So that helps you with the FCC process that we've just been talking about. But instead of it being on ton scale, it's on milligram scale. So it's all quite interesting. Hopefully it's interesting, and hopefully it hangs together. So knowledge of the preparation and characterization of zeolites I haven't covered. That's why it's in red. Okay. Will I ask you about that? Well, I might, because I'm nasty sometimes. And they basically are given to you in the paper at the back as an explanation of what zeolites are, but you could look up the preparation of zeolites. But I can tell you how you make a zeolite now in about 5 seconds flat. Caustic sodium hydroxide with a silica source and alumina source. You put them together. You put them in a bottle. It's very similar to that blue bottle that looks like it's got milk in there. Actually, this one is a very good example. This young lady's texting away, but we won't mind that. Hello. So that is equivalent to the size of autoclave that I use. Imagine that with a liquid in it, which is now caustic plus an alumina source plus a silica source, mixed together, and then left. Leave it for 24 hours to 72 hours to cook in the right proportions, and you make zeolites. Yes, it sounds simple, but only when you've got the preparation method. It isn't easy to make new ones, but that's how simple it is to make a zeolite. It's a stainless steel reactor with a PTFE lining, and you can look that up. And I used to have a whole loads of slides explaining how to make them, and you guys just glazed over even more than normal, so I took them all out. But you can have a look at how you make zeolites. There's a lovely description of that. I hate to say it in Wikipedia, but there is. And then the last bit that I want you to focus in on, because you've done design and you are engineers and you will have interviews, and is the knowledge of zeolites within a refinery process. And that's that. So I'm going to close that, and then I'm going to hope this slide works. And you had left extra time for a reason. Aha. Now this is all up on Blackboard. Trust me, I spent the best part of 3 hours on Monday just digging the right file out and checking that it worked. So when you're trying to build a first order model of something, do we know what we are trying to do? Where do we start? And what do we know? And obviously I've covered up the answers. Is it exothermic? Is it endothermic? Remember, it's on Blackboard, so don't panic if you don't write everything down. The slides are not in the booklet. They're on Blackboard, so don't look for them. Find a spare page if you want to write some notes. Bless you. Where do we start? Is it exothermic, endothermic? Is it a differential or an integral reactor? Right then, you lot. Differential reactor, what does that mean? Go on. It's something to do with conversion, is a hint. Sort of a muttering in the middle that sounded about right. Low conversion, less than 10%. 5-10% conversion, very low conversion. Why are we doing it? Because it's such a small amount that we don't want to use any complicated maths. We just want to measure the difference between two things. So if you're looking at a reactor that's a long length, you can break it into lots of little lengths. And eventually you get very small, small enough just for it to be a number minus the number in minus the number out. The trouble is, if it's a high conversion, it's not going to play ball all the way down the reactor, and you're going to have an error in it, but it's going to be a first approximation. Design is about making your best first approximation. A differential or an integral reactor. Integral, greater than 10%, greater than 20%, depending on where you read it, conversion. Do we have some heat dispersion in the bed? If there's heat and there's energetics, the heat dispersion in the bed is not uniform. So we have a temperature drop or a temperature rise. We have hot spots or we have cold spots. That's if the energetics is such that the number is greater than what? Delta H is greater than? Any idea? Okay, so if you're in the orders of tens, 10 to 20 to 30, that's not too severe. If it's 100 to 200, okay, then it's either a serious exotherm or a serious endotherm. Remember the slides with the explosion in it. So what does K observed mean? There's the rate constant of the processes that we define, but K observed is what we see as an average of all the processes that have taken place to get that data set. Not K of reaction, not K of the surface reaction, not K of the diffusion, a K of everything. E apparent, same thing. We've measured it. It's the E observed or it's the E apparent. I used observed in class. I've now confused you by putting apparent on there. It's the same thing. It's an average of the processes. Is it a large number? Does it change with temperature? So remember the graph that I was most insistent that you remember, and I now left my pen in my office. Lost. So remember, I'll do it by eye. So remember that a normal Arrhenius is a negative slope that's quite steep. Then there's the diffusion limitation plus the reaction, and then it goes flat. If it's flat, it's mass transport limited, so it doesn't matter what temperature you're at, there is no real change in the rate for an increase in temperature. If it's like that, it does exactly what it should do with Arrhenius. So are we surface reaction or are we something else? Finally, how do we now proceed? This is where you are at now. And if you've not written down that little checklist, it is on the slides that are up on Blackboard, but it wouldn't kill you just to say, have we done those things? Do we actually know that? Have we picked up on the fact? Because if you have, you're beginning to be engineers, but you don't need to have read anything. You've got it in your mind. Looking at a scientific piece of paper. They will automatically go, boom, 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 checklist. Right, okay, let's go with a plug flow reactor because it's the best, because it's the highest concentration, so it's the most efficient. We'll go with plug flow reactor. Then what do we do? Okay, that's it. If that seems too simplistic, I apologize. Next step. Integral reactor. Well, you remember this. This is the straightforward equations from second year, and you remember, you rearrange it, you end up with something like this. That is your conversion. So that's your overall conversion, which is in minus out over in. So that's the standard thing I talk about all the time, and that rearranges. Straightforward plug flow equation. So it rearranges like that. And you can do all that, and you've done all that many times. You might not remember that you've done all that, but you have done all that. Key thing at the bottom is this equation here. Volume of reactor, volumetric flow rate, rate constant, which we'll call an observed rate constant, but we'll call it a reaction rate constant, log minus 1 minus XA. Should have a minus sign in it, so that's 1 over 1 minus X. So what do we know? You've looked at the literature. You've looked at a reaction. You can't find any information. You come asking me, you ask other people, that's fine. I always do the same thing. Oh, I'm really sorry, but I don't know what I can do about that because I don't know anything about it. So I'm really sympathetic. Obviously not. Okay? So what do? You look at something similar. If you've got a molecule that's a C3 and you're doing C4, you look at the C4 and see whether you can find any data. If you haven't got a C4 and a C3 because you've never heard of these molecules and it's all oxygenated and it's all bio and it's really a problem, you go look at something very similar. You might start off by assuming that it's a hydrocarbon. There'll be tons of data on a hydrocarbon. Then you'll look at a molecule that's got oxygen in it compared to the hydrocarbon, and you'll say, oh, it's changed that property by about that. I wonder if that's true for the next molecule up, and so on and so forth. You make your best guess if you can't find it. Remember, what's the textbook you're supposed to look in? That's zeolites. Forget that one. What, yours? Did somebody say yours? Very good. Whoever said yours, yes. So the thermodynamic data book, yours. YAWS. So we've got that. That's 2C. So what have we got? We've got the conversion that we know happens because we've got XA, and we've got the volume and the volumetric flow, but we might not have the rate constant. Now then, this is all CRE on a page. Depressing though it may be, that's what it is. So we've gone from the top equation. We've assumed that we've got a rate of reaction and we're going to feed something. In this case, it's methyl cyclohexane, and we've got our rate equation, which is equivalent to that. X now equals that. The weight of the catalyst is going to look like area times the length times the density times 1 minus the voidage over the flow rate. We know that. We know that. We know that. We don't know that. We know that. And we measure that at the end of the reactor. So we've got everything but one thing, the rate of the reaction. And that's how I calculate the rate of reaction. And now you guys then interpret it and turn it into a massive reactor. When I've only done it on a few milligrams, you then scale it up something like 100,000 times, which is scary enough for me. But you do it, and you do it efficiently, and you don't tend to blow yourselves up that often. You do blow yourselves up, as I was looking in Tom's lecture this morning for lectures for you. I couldn't find it, but I found out how many explosions were in Texas in 2009. It was a lot more than I expected. About 30 deaths, in fact. So that's an aside. So what you do is you set up some reaction. And this data is in your handout as it happens. It is in your handout, and it's the slides that explains the reaction. And it's the bit that I never covered. And if you want to have a look, you can have a look. I'll point it at it in a minute because I can see it in here. So just so you know, it's after Langmuir-Hinchelwood. It's before the zeolite bit. It's before the bit on steam reforming. It's chapter 4, chapter 5, and it's the pages at the back. And basically it refers to that. And the data is all there. Everything that we're looking at now is actually there. So if you want to turn to those two pages, you can do since you're here. And you're a captive audience, as they say. Pages 5.7, 5.8, 5.9, 5.10. So I just want you to know that that's the full breakdown. You can read that in your own time, but it's a very good... My student wrote that for an exercise that we used to do in CRE 3 or 4 years ago, that the students, you guys, used to sit in computer clusters and work on for hours upon hours upon hours upon hours, and used to say, it's too difficult, Dr. Garforth, we don't want to do it anymore. So I stopped it, and then the next year everybody said, oh, you've not done that exercise, it's really, really good, I wish you'd done that because I had all this thing. Well, I put it up on Blackboard for you so you can see the answer to the thing they were doing. But key things are, all you know going in is what you see on the top. So you've got the temperature, you've got some flow rate, which you have set or I have set. It's a lab reactor, remember, so it's my reactor, it's my domain. So it's small amounts of catalyst, but you've got a flow of hydrogen, and I tell you what it is. So I tell you that we're going to get 15 to 30 to 7.5 mils per hour of a liquid feed, and we get 200 to 800 mils per minute of a gas feed. And I gave it the class, and the mistake is always the same. You calculate the gas one wrong. Every single time you go to PV equals nRT as if it's God's gift to everything. Okay, yes, I know it's an ideal gas law. Yes, I know what it is, but it's not the right way to do it. It's already a volume. So if you're doing 400 mils per minute, how many mils per hour is that? 2.4 liters, is it? 224, yeah? 400 mils per minute times 60, 4,000, 24 mil, to 24,000 mils, okay? So 24,000 mils per minute. How many liters per certain things equals a mole? 22.4 liters at STP, 24.1 liters NTP. Why the subtle difference? One's at absolute zero, when I said zero, not absolute zero, sorry, so it's at 273, and the other's room temperature. It's most pragmatic of engineers to use NTP, normal temperature and pressure, not the 0 degrees C. So you calculate it and you can come up with a number of moles, and it's two lines. You guys go to equations and you're looking for the total number of moles. You do all sorts of calculations, but you always calculate the volume of gas wrong. There's nothing to it. The liquid you get right because you've got density in there and so on and so forth. The conversion is at the bottom. So for these three conditions, there's a hell of a range of conversion, but it's an integral reactor. You can see it there. So we have all this useful data, which is all beautifully laid out for you, and it's said there, and you're tired, and it's Friday. And we have a little picture of the reactor schematic there to show you that we've put a thermocouple down the middle of a bed, and the bed looks like that, and those are all the dimensions. All these things you'd be expected to calculate. I've broken it into steps so you can do it. In the spreadsheet, you've got the answer. So you really don't need to follow other than to say everything's within Blackboard for you. Remember, very first exercise was an equilibrium reaction, and we were asking you to do equilibrium reactions and calculate the mole fraction in, mole fraction out. And this is where it all goes. We've got an isothermal reactor, so we've got different temperatures down the bed. This is real data. This is not fake. So you can see that in this reactor, there's a temperature drop in Kelvin there of about 50 degrees C. So we have to use an average between the wall temperature at the top and the one in the middle, because we've only got one thing to choose, an average. You do that. You set up that equation. You then set your Excel spreadsheet. You've got everything you need to know. You're going to estimate a temperature. You're going to end up calculating that. And you've got your useful data, and it's all filled in for you. You calculate all those numbers that are there, and you end up with that. So that's the answer. It doesn't look very good, does it? Okay. So what we've done is we've modeled our reactor. We've put the numbers in, log 1 of 1 minus x versus v over v, which is what CRE2 tells you to do and what I've been telling you to do, and there's no correlation. So we play around with it a bit. And that's what we get. So in the end, I've got graphs which contain 2,000 data points from 2,000 individual reactions that all fit within a 5% limit, and I've got a paper that says that I'm good at doing that sort of thing, which is fine. Means my PhD student's good at doing that, not me. Okay? So what's the purpose of the model? What's on those axes is the purpose of that model. X versus x. X is the observed, which you know because you see it. X is your prediction because of your model. So what you have on Blackboard is all those slides with the numbers crunched for you in easy steps, because I've shown you the steps in that PowerPoint presentation. The next thing you've got is the final spreadsheet. And it looks something like that. First run, 9 runs, own catalyst. That's my catalyst, okay? And we've got an activation energy, and it's 56,500 kilojoules per mole. That's a bit high. Okay. We've got a voidage of 0.5 that you're familiar with, and we've got a rate constant. And we look and we